And oh, I've got multiple ones going. I am currently recording. That's good. Starting the PowerPoint. All right. Stoichiometry, calculations involving balanced chemical equations. The word stoichiometry, well, it's just awesome because like it's got like so much cool stuff in it. The last part of the word, metry, that simply means to measure anything, right? Another word that has metry in it, telemetry. If you're measuring, where a plane has to go and how it has to point, it's measuring the angles of that particular type of stuff. I'm trying to think. Any other words that end in metry that you've heard of before? I know there are. I can't think of them right now. Symmetry. You're looking for lines that are based off, but again, it's a measurement of some sort. It's a measurement of similarity across a thing. Yep. Geometry, measuring angles, the measurement of angles. So it simply means to measure things. The middle part of this word, chio, right? Chiom, right, is chemistry. That's the same prefix that we use for chemotherapy, right? That just simply means chemicals, right? Chemotherapy is when they treat cancer with chemicals, injection of chemicals, as opposed to radiation therapy, where they will shine certain types of radiation at the tumor. So that's a different type of therapy. So this is like chemo, right? And the first part, and again, I've looked it up many times and I keep forgetting, but it has to do with again, counting the chemicals. So this is all about counting chemicals in a balanced chemical reaction. Okay, moving on. You don't need to rewrite that. You can write that bullet because you've already got the heading above. And you don't need to write what's in italics there. Just write the bullet. And if you wrote ahead, then you've already maybe wrote what's in the italics. No? You figured that would be a good place to stop? Good thinking. It's the mathematical procedure for calculating quantities of reactants and products involved in reactions. And quantities in chemistry, mole, all right? Quantities in chemistry are moles. That's how we count things. Remember when I first introduced the mole to you, we talked about the dozen. That's quantities in baking. I don't know, does that make sense? No, baking, dozens, I don't know. Quantities for pencils in dozens. When it comes to chemicals, we count our chemicals by moles. Entities are too small. They're not useful. So we like moles. Now notice it says here of reactants and products, which means we need a balanced chemical equation in order to understand this. So we're going to learn a new calculation that's going to go along with our old calculation. That'll be tomorrow. So today we're just learning the new calculation that allows us to calculate various things in a chemical reaction. A balanced chemical equation is like a recipe for cookies or cake. It tells us how much reactants are needed and how much product will be produced. All right, so many cups of this and so many tablespoons of this to result in one cake. And so you can think of that as being a series of ratios on how we can put together a cake. If we want to make 2 cakes, what do you have to do to a recipe? You double the recipe. So if you needed, 5 cups to make 1 cake, you'd need 10 cups to make 2 cakes. It's exactly the same in a chemical reaction. If you want to make water, you need 2 molecules of hydrogen for 1 molecule of oxygen to make, 2 molecules of water. If you want to make twice as much, you double everything. So it's all about ratios. Okay. So you can write that down. The most important thing when doing a stoichiometry problem is writing the balanced chemical equation. And I've been a little evil on this one. Why have I been evil? Because it's not balanced. Isn't that fun? We know how to do that. We've learned that. So let's go ahead and balance this as well, and let them have a chance. Again, good to work in pencil. You got it? Then if you make a mistake, you can always fix it up. I would likely use the 2-3 maneuver on this one to balance this up, because I'm seeing the 2 and the 3 there on the H. That would be my plan. And because Amy would pout if I asked someone else for the answer, Amy, what do you have? 3, 2, and then the 2 is taken care of. Excellent. So in this particular recipe, for every 1, well, let's just write this down underneath. For every 1 mole of N2, we need 3 moles of H2, and that produces 2 moles of NH3. Why doesn't it make sense? You want them to add up nicely. Yeah. And it isn't actually an addition. The only things that add up are the number and types of atoms. If we were totaling up all of the atoms, then it will add up. But here, we're breaking apart 1 molecule of N2. We're breaking apart 3 molecules of hydrogen into individual atoms, and then we're sticking the parts together again, which means they might fit together in different ways such that the moles don't add up. So, no, it doesn't add up. But again, you know, think about a cake. If it takes you, probably a big cake, it takes you 5 cups of flour. Okay, I like making pizza dough. I make pizza dough. So if you take 5 cups of flour, right, and you add in, you know, a half a cup of yeast to make, you know, maybe 8 pizzas, 8 large pizzas. You know pizza. You can talk in pizza, can't you? Then you don't add the 5 cups plus, you know, the half a cup of yeast to get 8. That doesn't add up, but in the end, it makes 8 pizzas. Does that make sense? You see what I mean? Just because the individual, you know, ingredients don't add up, it means that you're not just totaling them. You're making something new, like pizza. All right, and don't burn yourself, as we all know. Okay, so what we can do is we can get lots of ratios out of these particular numbers. And I have to check my little thing here. Okay. So now what we're going to create is a new ratio called the mole ratio. All right? The mole ratio. And it's very easy to create the mole ratio. Here's an example of a mole ratio. If I want the ratio of N2 to H2, and for those who have taken this is going to look quite different than what you're used to, because I'm not making it as a conversion factor, but you could still use that method. You can still use conversion factor method if you'd like. Here's the ratio of N2 to H2. It's going to be 1 to 3, right? I just created a ratio. Are we okay with ratios in mathematics? So what I did to get this ratio was, because it's N2 to H2, there's a 1 right there, which we don't see. I'm going to draw it in. 1 to 3. N2 to H2. You see how I did that? So I can create whatever mole ratio I would like to, or that I need in order to answer the question. So here are some others. Here's another mole ratio. What would be the mole ratio of H2 to NH3? And I can relate reactant to reactant or reactant to product. It doesn't matter what I'm comparing. I'm just picking out ratios. What over what would be the mole ratio for this? What over what? Alexis, what do you think? 3 over 2. 3 over 2. For every 3 H2s, 2 NH3s will be produced. And there's no real, I'm not picking these out in any special way. I'm just picking 2. Let's just do one more just for fun. I guess we can pick the outside. Let's say, what if I knew something about NH3 and I wanted to find out something about N2? What would be the NH3 to N2 ratio as presented in that particular situation? What would be its ratio? John, what do you think? What would be the NH3 to N2? 2 to 1. You have 2 to 1 ratio. Are we okay with this idea of a mole ratio? The mole ratio always compares 2 things in the chemical reaction, and it can be reactant to reactant. That would be like making your pizza and saying, okay, we need, I've got 10 cups of flour. How much yeast do I need to take care of this? So you can figure out how much other reactant you need. Or it can compare reactant to product. That'd be like saying, I got 8 cups of flour. How many pieces can we put together before we have to close up shop, right? So you could figure out how much of the other one you need. Okay. All right. Now you don't have to write anything down. Actually, rewrite the balanced chemical equation. I'm just adding on to the mole ratio at this point. Now, let's say that we had 3 moles of this, and you'll notice I've wrote it underneath N2. I have 3 moles of N2. The question might be, how many moles of NH3 can be made? Now, these are the types of questions that we deal with. Again, I got to balance this back up because I copied and pasted the unbalanced one. So I believe I need a 2 and a 3, correct? Okay. So make sure you have that in there. So very often in a question, we will be given information about one of the reactants, and we will want to find out something about either another reactant or a product. I like to write in maps. You guys may have noticed that when we were doing the product. I like to write what unit we're starting in and where we're heading. So I like to draw a line in here to represent the fact that we're starting with 3 moles, and we want to find out how many moles of the NH3 there are. Now, I have to make a little change here because I'm bouncing back and forth between the way I do it in the grade 11s and the way I do it for you guys. Instead of a question mark, I want you to put an X. We're looking for X moles. We're going to solve a little equation in order to get that. No, that was a question mark. Okay? So we know how much N2 we have, and we want to solve for X. Now, this is quite straightforward to set up this particular equation. Again, I need to think in terms of, I got to be careful, because I got to have the X on the top. I got to have the X on the top. I have to start with this. Because I want to find X over 3. All right? X divided by 3 is going to be the same as the mole ratio. 2 over 1. 2 over 1. All right? Again, I haven't taught it this way in a long time. This is the way I used to do this years ago when I started teaching, even with the advanced groups. But X over 3, X divided by 3, is equal to 2 over 1. So the X with the 2 and the N with the 1. The mole ratio we used was NH3 over N2, right? NH3 over N2. The X was what we were looking for, NH3, What we know we put on the bottom. Now, we have to solve this equation. Does anybody know how I can isolate x by itself? What do I have to mathematically do if I have a ratio like that in order to get x by itself? And this is where we've got to do a little bit of math. But if we set it up the same way every time, we should be able to get the answer. What do we have to do? What? No, I'm not multiplying x by itself. If I were to multiply x by itself, I'd get something called x squared. But I have to multiply something. I have to multiply something. Yep. Yeah, I have to multiply 3 with 2. That's correct. Now, there's two ways of thinking about this. Mathematically speaking, we need to get rid of this 3. So we're going to multiply the top times 3. All right? And then we'll do the same over here, times 3. Because in mathematics, what you do to one side, you have to do to the other side. Now, I'm going to show you a little shortcut to this in a minute. What that does is it cancels out the 3, all right? That leaves us with x, and then I've got 2 times 3 divided by 1. Okay? Now, let's go back and look at that, and let me show you a quicker way to do that. If I have x over 3, 2, 1, some teachers call this opposite operations. Have you ever heard of that before? Across an equal sign, when you want to move something, you do the opposite calculation to what it was on the one side. This was divided by 3 on the left side. What's the opposite operation to divide? Multiply. So when we bring the 3 to the other side, it becomes a multiply by 3. Okay? So I wouldn't think of it like this. I would just write the x. I would have the 2 over 1, and then I would do the opposite operation. You see how that works? The divide by 3 became a multiply by 3 on the other side. All right? In the end, what is x equal to? 6 over 1, and when you divide something by 1 in your calculator, 6, right? It's equal to 6 moles. Okay? All right? Let's do another example. So I'm going to clear it out to another one. We're using the same equation, so you can just rewrite it again. This is 3, and this is 2. Now, let me set this up a little differently this time, because I know where we're going to go tomorrow with our lesson. Tomorrow with our lesson, we're going to start with something like grams. And we're going to need to use this equation to find moles, so we could then use the mole ratio. This time in your question, I want you to imagine that you have 2 lines underneath your balanced chemical equation. And because your paper is full of lines, you don't have to imagine that you have 2 lines, because you have 2 lines. The bottom line, I call the mole line. That's where I put any information that I know about moles. Okay? In the top line is the gram line. And we're going to use the gram line tomorrow to help us solve these problems. Today's lesson is just about using the mole line. That's it. So we're only going to use the second line. So in this case, and again, I'm just making these up as I go just for practice, if I have 1.75 moles of this product, the question might be, how much H2 do I need? X moles of H2. That's what I'm looking for. Notice how I've wrote them both in the mole line. That's where I want to put my moles information. I then put an arrow. And now I'm making the map. What I'm doing is I'm building a map with the chemical equation to help me think it through. To go from moles to moles, we use a mole ratio, which means we're going to use that X over whatever is whatever over whatever. And we're going to build it the same every time. So from my mole line, X over 1.75, X over 1.75, right, is equal to, what is my mole ratio going to be in this case? Which goes where? Go back to your previous example. Notice in the previous example, and I wonder if I can go back. Let's go back to the previous example. I can go back. Notice X, X, 2, 2. You see that? So whatever is on the top, the X, I'm putting that number from the balanced chemical equation with it. X is with 2 and 3 is with 1. You see how that kind of works? You're going straight up to see what goes beside it. That, I guess, might be a little confusing. X is with 2 and 3 is with 1. All right? X is with 2, 3 is with 1. X is with 3 and 1.75 is with 2. Okay? Yep. That's a number that I would have given you in the question. We're going to do full questions here in a moment. That's one that I just gave you for practice. You need to be given a piece of information at the beginning in order to do a problem. Okay? What am I going to do with this 1.75 on the other side? It's division here. What does it become on this side? Multiplication. So you know what you can do if you want to write this quicker? You can just do this and put times 1.75, and you don't need to rewrite it. Just move it. All right? Then just run that through your calculator. 2 times 1.75 divided by 2. And what is X? Sorry, 3 times 1.75 divided by 2. We have a number? Sorry? 5.25. 5.25 moles. And in this case, it would be moles of H2. We don't like that number? Did we not divide by 2? 2.625. My eraser doesn't work. 2.625. I think maybe we would round that, but we'll write it down. 25 moles of H2. Do we like that number? Conrad, did you figure out your mistake? Okay. All right. So X is with 3, 1.75 is with 2. X over 1.75, 3 over 2. Okay. And let's actually now do some questions that appears in a question form. So I've told you the tricks. Now I'm going to give you a question and we'll set it up. Now we call these mole-mole calculations because we're starting with moles and we're ending with moles. Tomorrow we're going to add another step. We're going to add grams to the mix. We talked about the mole ratio. This is the same reaction, but we'll do it again. We'll do it one more time. I guess in this case, what you're now doing is you're translating the information out of the question to put into your lines. Today's lesson, it's all moles, moles. So we're just using the bottom line. Find the moles of ammonia that would be produced if 2.75 moles of nitrogen reacts. Where am I putting my number, and where am I putting my x? That's what this is all about. Where am I putting my number and where am I putting my x? Yep. Yep. And I'm going to leave a space just because we're going to practice, because tomorrow there's going to be stuff we're going to put in it. 2.75 moles. And where's my x? Yep, the 2NH3 is x moles. I like to draw the map. What do we call this thing that we've been building all class long? Yep. Mole ratio. And we get it from our numbers. X over what? Yep. X over 2.75 is the same ratio as? Bethany, what do you think? 2 over 1. X over 2.75 is equal to 2 over 1. That's the ratio. Bring it up to the other side, multiply it, and you've got x. So I guess the way to think about it, x over 2.75 is the same as 2 to 1 ratio. So you line them up right beside each other. And I would just write times 2.75, get rid of that, x is equal to. Yep. 5.5? 5.5 moles. And you know what? To be thorough, you should say what you found, moles of NH3. Because then it says what we're looking for. That's kind of like your therefore statement. When you're doing questions for me on assignments or tests, I don't need a therefore statement. I just like a box around your final answer. That tells me you calculated 5.5 moles of NH3. Let's do one more example. And I had another one that had NH3 in it again, but let's do a different one just for fun. Now, in the university chemistry, very often I do not supply the balanced chemical equation. It's the responsibility of the chemist to know that. And I tell them that on a test, I probably give you 50% of them with the balanced chemical equation and 50% without. For you guys, that ratio would be different. I'd likely give you the majority with the balanced chemical equation because I want you to be able to do the math. But there might be one that doesn't have a balanced chemical equation. And at that point, I'm trying to see if you can do the balanced chemical equation. What I say to those students, if they struggle with the balanced chemical equation, if you can't start the question, you can't finish it. And I always say, if you ask, I can't get the balanced chemical equation, could you tell it to me? I then would write it on your test paper in red, and you would simply lose the marks that you would have got for balancing it. So let's say you were getting 3 marks for balancing it and 3 marks for calculating. You'd only be able to get 3 marks on the question, but you'd at least be able to proceed, right? Because as you're realizing, if you can't get a balanced chemical equation, you're going to be done with these types of questions. So it wouldn't be very many, but I might put 1 on the test to see if you can put it all together. What are the reactants in this question? What chemicals are reacting together from the words? What are coming together? What are the chemicals? John, you got an idea? Hydrogen and oxygen. Do we know we've got the formulas in there for those two. They're both Hofbrinkels, so H2 plus O2. What's our product? H2O. Yeah, H2O, excellent. Does anybody balance that? We got it balanced? Yep, Conrad? I don't know if I want to put that. You would have then had to do something like 4-2-4. Is that what you did? 4 and then a 2 and then a 4, but that's too many of them. We can cancel it down. Yeah. 2-1-2. You might have had 4-2-4, right? And you know what? If you had 424, your math would still work. The mole ratio would just be twice as big and you'd get the same answer. It's just it wouldn't be balanced in the simplest way, but it'd still be correct. Where is my number and where is my x? Where's my number and where is my x? Yeah, the number goes with water. So 1.25 moles, that's how much we want to make. And where's the x? Under the hydrogen, x moles. How do we do this? We use the mole ratio. That's what this is all about. X over 1.25, x over 1.25 is equal to, could somebody please, this is what I'm really checking to see if you understand. We go to Alexis. X over 1.25 is 2 over 2. 2 over 2. 2 over 2. So get that out of there, 1.25. And don't confuse that with an x. X is equal to, and they cancel out, right? So we're going to end up with 1.25 moles H2O. All right? Now, I must admit, I was stumbling over some words at the beginning of this lesson because I haven't taught it in this form in quite some time. Does everybody understand? Everybody kind of seeing the way we're building that mole ratio? Yep. Oh, it's H2. It's me making a mistake. Good stuff. I'm busy thinking and talking. That is H2. That's what we found right here. Correct. Good job. Thank you. Any other issues? All right, again on Google Classroom, I've left a sheet for you that have some answers to it, so you can go ahead and work on those. You'll notice this isn't the type of thing that's easy to type in. This is the type of thing that you got to write down. So you're probably doing practice just on paper, making reference to the, put your date down and then you'll know where to find the sheet, that type of stuff. This stuff is still just practice, which means Mark isn't going to do it. We know the way that works. But the rest of you should, because we're not all, Triple Crown winners like Mark. All right.